Hello, welcome to the course Mathematical Foundations of Computer Science. We are going to study Unit 3 Algebraic Structures. So let's try to understand what is this algebraic structures and what is the use of this in computer science. This is very widely used actually in cryptography. Cryptography is one branch of concept in computer science which deals with securing the data, or I would say information security. So these algebraic structures are widely used in cryptography, right? So it's kind of it's based on set theory only. It is based on set theory only. We have studied in set theory about sets and relations, right? So here also we talk something about sets and relations. So let's try to explore what is called an algebraic structure, what are the different types, and why we have to study this. This is very widely used in cryptographic algorithms or cryptographic techniques. So what is an algebraic structure? A non-empty set S is called an algebraic structure with respect to binary operation star. Okay, it means I have a set S with elements A, B, C. Okay, and along with this, I will tell, I will give an operator. I will give one operator, and I will say that these three elements of this set satisfy this property always, satisfy this operation always. Okay, so you are sending the elements and the operation which those elements is satisfying, right? So one property is closure property. It means if there are two elements A comma B which belongs to set S, if there are two elements A comma B which belongs to set S, then A along with that A, this star is not multiplication. It means any operation. This A star B should also belong to S. Let's see example. See, S set 1 minus 1 is called algebraic structure under multiplication. Here, this is multiplication. Why? You take this is A, this is B, you apply multiplication. 1 into 1 is 1, 1 into minus 1 is minus 1, minus 1 into minus 1 is 1. So, the result you see 1 minus 1, all are there in the same set S. Therefore, we say S is called an algebraic structure with over operation star. Is it true that S is equal to 1 comma minus 1 is called an algebraic structure over addition? No. Why? Let's see. 1 plus 1 is 2. We don't have that in this set. 1 minus 1 is 0. We also don't have this in our set. Therefore, the set S over addition operation is not an algebraic structure. It does not satisfy the property. Okay. So, here in this case, the binary operation star doesn't mean multiplication. Remember that. Right. So, what are the different properties of algebraic structure? Let's see one by one. Let's suppose a set G contains binary operation star. This can be a plus, multiplication, division, or minus. It can be any operation. Okay, it modulo operator or any operator. The star is said to be okay. So commutative. First property is commutative. If two elements x and y, if you apply that operation, and y and that operator if you apply, if both the results are same, then we say it is satisfying commutative property. If there are two elements minus 1 comma 1 and the operator given is multiplication, you see you do minus 1 into 1, you yield minus 1. This result, you apply 1 into minus 1, this also is minus 1. Both are equal. Then we say this set of elements minus 1 comma 1 satisfy commutative property over the operation multiplication. Next, associativity. X into y into z is same as x into y into z. If this is also satisfied for all the variables, then we say that particular set G satisfies the associative property. Next is very important, identity property. What is this identity? See, if you take any element from the set S, okay, if you take any element from the set S, and if you have a unique element E, if you have an unique element E, for which x into E or E into x should yield x. Okay, should yield x. Let's see an example. For multiplication operation, the element E is 1. For addition operation, the element E is 0. These are fixed standards. Why? Let us take a set. Maybe if I take 3, 2, 1 as one set. Okay, I have a set yes. Now, you see, I will take any random element from this. Let me take 2 into over the operation multiplication. For multiplication, what is the identity element? 1. 2 into 1 is equal to 1 into 2 is equal to 2. And this 2 is belonging to set X. This yes. Okay. So if you take any random element from that set, based on the operation, if you have the identity element, it should yield the same element X. Next is inverse. In inverse, if you randomly choose two elements X and Y from the set, you apply that operation, it should always yield the identity element. It should always yield the identity element. So there are total 5 properties in algebraic structure. What are those? First one is closure property, then we have commutative, associative, identity, and inverse. Okay. So there are different kinds of algebraic structures. First one is called semi-group, monoid, group, abelian group. What are these? I will skip these slides. I'll just go to this table. See, any set S can be called as algebraic structure if it satisfies only closure. It can be called as semi-group if it satisfies both closure and associative. It can be called as monoid if it satisfies closure, associative, and identity. It can be called as group if it satisfies closure, associative, identity, and inverse. It is called an abelian group if it satisfies all the 5 properties. So this, if you remember, it is very easy, right? This is what the explanation we have given here. If you see, semi-group means it satisfies closure and associativity. Monoid means 3, closure, associative, and identity element. Group means 4, along with that inverse. Abelian means all 5. Okay, all 5. Let's see an example before we go to the next concept. Let's see an example. Suppose I have a set, integer set, that is so on, -3, -2, -1, 0, 1, 2, 3, and so on, minus infinity to plus infinity. Let us check whether it is a semi-group or a monoid or a group or abelian group. Let's start from closure property. Closure property says that if you take any two elements from this x comma y, when you the operation given here is multiplication. Okay, the operation given here is addition. Let's take addition. The operation is addition. Okay, now over addition, you take any two random elements, add them, check whether the result is there here or not. Definitely it will be there, because it is minus infinity to plus infinity. So if I take -3 plus 7, that will give 4. 4 is there in the set, so it satisfies closure. Associativity, if I add -3 plus 7 plus 2, it is in bracket, it is also same as -3 plus 7 plus 2. Both the results are same, so it is satisfying associative property. Identity property, for addition the identity element is 0. So if I take 3 plus 0 is equal to 0 plus 3 is equal to 3. There is no problem at all in this. It satisfies identity. Inverse, if you choose random two elements, it should yield the inverse. Yes, it is also possible, because if you take -1 and 1, see, -1 plus 1, it is giving 0. -3 plus 3, it is giving 0. Therefore, it is satisfying inverse property. Commutative is very simple. Commutative means -3 into 2 is equal to 2 into -3, and that result -6 should also belong to this original set. Yes, it is belonging to there. Therefore, we could say that this is the example which I discussed now. Given set of integers minus infinity to plus infinity, over the operation addition, it is an abelian group, because it satisfies all the properties. Over the operation multiplication, there can be some limitations. Not all properties are satisfied. Over multiplication, it may not satisfy all the properties. Okay, that you can please try to see. So in exam, we can expect some questions like this. A set will be given to you, and the operation will be given to you. Find out whether it is an like this, whether it is in semi-group or monoid or group or abelian group. So you have to verify these properties and find out that. Till now, if you see, in all these 5 algebraic structures, I am talking only about a set S and only about one operation like this. See, one set and one operation. So if this set satisfies all the 5 properties over addition or over any operation given, we call it as abelian group. Now next concept is rings and fields. Rings and fields. What is this ring and field? See, a group means given a set and one operation. Whereas rings and field, ring means given a set G or given a set S, if it is satisfies all the properties over addition, plus the same set S satisfies few over multiplication. You understand my point? I will just go into this slide. If you observe, what is a ring here? A ring is a set R which is closed under two operations, plus and multiplication. So R, it's an abelian group over addition. It means it satisfies all the 5 properties over addition. Along with that, the same set R also satisfies some conditions over multiplication, like this: associativity and distributive. Then this kind of a set is called a ring. Okay, a ring here talks about two operations, not a single operation: addition and multiplication. Over addition, it satisfies all 5 properties, plus over multiplication, it satisfies 2 properties. Then we call such kind of a set R as a ring. Now what is field? Field is little more extension. If I have a set R, it satisfies addition and multiplication. It satisfies all 5 properties over addition and all 5 properties over multiplication. That's why we say a field is set F which is closed under addition and multiplication. Over addition, it's an abelian group. Over addition, it's an abelian group. Over multiplication, except 0. Okay, so this is about ring and field. Groups talk about single variable, a single set and single operation, whereas ring and field talk about single set but 2 operations, that is addition and multiplication. So this is about algebraic structures, different concepts we have seen. This has wide application in cryptography course. So in unit 4, you are going to solve lot of problems related to cryptography. We are going to do lot of mathematical primitives which are required for cryptography. There we will be using this concept of ring, field and groups, right? So we'll end it here. We'll see in the next lecture, we'll talk about the cryptographic primitives. Thank you.